Hello. Good afternoon, good evening, and good morning, whenever you're listening to this. This is for Econ 103, and we're now taking a look at some empirical work other than the empirical work featured in our main textbook, GLS. Specifically, we're looking at some ideas coming from Asimoglu's Modern Economic Growth textbook. We're using this because this is a great resource as a summary for all of the main kinds of work that has been done or can still be done using growth framework such as the Solow growth model. And all other growth frameworks basically are based on the ideas here. So it's very useful moving forward, right? The Solow growth model or extensions interpret both economic growth over time and cross-country in output differences. So in these slides, we will focus on the cross-country output differences interpretation with a little bit of growth accounting in there. The economic growth regressions are mainly the regressions where you have where you can test theories about convergence. Those are the main economic growth regressions using the Solow growth model, and we'll be doing that hopefully in class because our main empirical paper that we will try to replicate is the Patel Sandifer paper, which is on estimating convergence across countries. Next, as Asimoglu takes pains to emphasize, the focus here is on proximate causes of economic growth. Okay, so approximate causes means the most direct causes of economic growth, which are capital accumulation, human capital, which is a major focus of these slides, and also technology and technological growth. Okay, some of those proximate causes we have certain levers to influence, such as capital accumulation and human capital accumulation. But in a sense, for now, at the very least, our understanding of how to influence TFP or labor efficiency is there's no direct lever on that. And I say as of now because right now we have not yet focused on what's called endogenous growth models, where growth can occur endogenously in a sense because of it's a natural byproduct of accumulation, right? So it's not an exogenous growth like we have here in Solow, but an endogenous growth. And accumulation is something we can potentially influence. Okay. Couple of necessary things to note here. These slides and the Asimoglu chapter in the modern economic growth textbook, that's a graduate school textbook, and there's a lot of material here that we won't use at 103. Feel free, of course, to read through the original textbook. We have a copy in the library, I think, and there should be like PDF copies online as well. And not all of the slides here will be the subject of our first long test. Only a few of them. So I'll be talking about slides which I expect you to know. The other slides, feel free to read them. They're super interesting, of course. Okay, let's continue. So first, let's review growth accounting. So growth accounting is simply accounting where the changes in GDP or Y come from. And like we've mentioned, perhaps you've heard this in 101, there's only really three main sources, right? It's either coming from K, L, uh, and A, right? Generally speaking, that's the two different factors, and finally, some sort of efficiency or technological change. Okay, so those are the three sources of change in Y. Okay, and combined with competitive factor markets, so that's an assumption, right? Combined with competitive factor markets, we can use the production function here into a growth accounting framework. Okay. So firstly, you can totally differentiate this equation here. And I would like, we covered total differentiation and time differentiation in class. So I hope that you guys are able to derive this expression here. Okay. So it should be very, very clear, very easy. So first, Notice that the denominator y, there's a y here, and then there's a y in each of the three terms, the three sources of economic growth, right? That's why it's divided by y, because the y's in the denominator are all coming from that. Okay. So if you can imagine, therefore, the left hand side is really just y dot, which is the derivative of y with respect to time. And then this first term, let's just talk about this first term. This first term is the derivative of this production function with respect to a. That's fa right there, right? And notice we are using the familiar trick where a in the top and a in the denominator, so those actually cancel. So what's in the first term really is f of a, and then you get the derivative of a with respect to time, which is a dot. So you can do this for all three sources of economic growth, and you'll get these terms here. Denote the growth rates of output, capital stock, and labor by G, okay, y dot over y, G sub k dot over k, and G of L dot over L. Define the contribution of technology growth as X, which is this one, this term here. This A dot over A, that's the growth in A, or technology. And then this one, FAA over Y, is sort of the weight of that change in A in overall GDP growth. With competitive factor markets here, W, F of L, and R, F of K, you can replace F of L and F of K with W and R. And note that we have factor shares here, alpha K as RK over Y, and alpha L equals WL over Y. Putting these together, the fundamental growth accounting equation in one becomes the following. So notice that this is G, or Y dot over Y. And this is the contribution of TFP. This is the change in A. And then notice here that the change in G, or G, which is the change in Y dot over Y, you subtract the contribution of capital, and then you subtract the contribution of labor. And whatever remains, because look at some positive number, and then you're subtracting two numbers here. Whatever is remaining, that is what's attributable to TFP. So here's your TFP estimate, that total factor productivity growth, which is just G minus the contribution of capital here, minus the contribution of labor here. Okay. Let me just move this up here. All terms on the right-hand side are estimates obtained with a range of assumptions from national accounts and other data sources. So G, which is the growth rate in real GDP, that's data, right? Alpha K and alpha L, that's also data. We talked about how these are just shares, and you can calculate this in national income accounts. GK and GL are perhaps the two important pieces of information here. These are measurable, but Asimoglu will take pains to assert that our measurement of capital and our measurement of labor may be problematic. Okay. So we don't have to put too much of attention here in Growth Accounting 3. All these next couple of slides will say is that we can translate this continuous time growth accounting equation into a discrete time version, which is this equation 4 here. Okay, so notice that this x hat, which is an estimate of TFP, is just GT, the growth in TFP between periods T and T plus 1. So that's possible. And you have the same interpretation here for GK and GL, which is the growth between T and T plus 1. Normally, when you're estimating estimating TFP using growth accounting, because we're using national income accounts, which are discrete in nature. This is how it's computed, right, in practice. Okay. And here we notice that usually the alpha that we'll be using is some sort of, average over time, as we'll notice that these alpha Ks and these alpha Ls will generally, even though we're saying that in Cobb Douglas that they're fixed, There'll still be some changes over time, wiggles in the value of the share of capital and the share of labor. So we will try to get an average over, neighboring periods here, t and t plus one. Okay. So equation four is a fairly good approximation to the continuous time version when the difference between t and t plus one is small and the capital labor ratio does not change much during this time interval. Okay, so there's a natural approximation happening when you're working with discrete time. Okay. A couple of other interesting things here. A number of pitfalls were recognized, right? So this is an interesting famous quote by Abramovitz. It dubbed X hat, which is TFP growth, right, as the measure of our ignorance, is everything that we don't know about the sources of economic growth. The growth in Y, is all lumped into TFP growth, X hat. The last slide, or not slide, but uh, bullet, I should say. Can't remove this thing. There. If we mismeasure GL and GK, okay, and the next slide will tell us what kind of mismeasurement it might be at play here, we will arrive at inflated estimates of X hat. Okay. We'll see how in a moment. So, growth accounting five, reasons for mismeasurement. So, for labor, what matters is not labor hours. So, that's typically how GL is measured, but effective labor hours. We call that. There is normally a Z term before the L. So, it's Z times L. So, that's effective labor, right? That's the important thing to measure. So we have to measure labor and also sort of incorporate the productivity of labor as you're measuring it. Okay? Because what you're really trying to do is to get the growth in effective labor hours. Okay? So it's important though difficult to make adjustments for changes in the human capital of workers. So we'll try to do that in a few of these slides. A slightly more advanced reason here is this measurement of capital inputs. So there could be a mistake or difficult to measure capital inputs. So in the theoretical model, capital corresponds to the final good used as inputs to produce more goods, right? So if you recall, C plus I equals Y, right? So I is just an additional capital, and it's corresponds to or is denominated in terms of the final good, right? So that's why Y is basically just investment, which is basically just capital, right? So that's what we know in the theoretical model. Oh, by the way, that's also true in uh, Solow, because in Solow, investment is just K dot, right? Or the change in K. But in practice, though, the final good or the final output good is not necessarily the important thing, because what we'll be looking at in practice is machinery. So it's not really a final good, right? It's machinery. It's more used as not just as a final good, but it's also used as an input to produce other goods, right? So in that case, you'll need to know the relative price of machinery and how that will change over time. Okay, so there's a complication. Okay, and that if you don't think about or incorporate this price of investment or price of machinery, then you will mismeasure the growth in capital inputs, right? Because the growth in capital inputs is just these capital expenditures. So expenditure is about the peso value of investment, correct? But if the price of investment is falling and machines become cheaper, you would then severely underestimate GK, because GK is meant to be not, strictly speaking, not the growth in capital expenditures, but the growth in real capital expenditures. Okay, which in practice we sort of use capital expenditures, but we would normally try to deflate it using, say, a CPI or the price of capital goods. Yeah. So this part, I would admit that you guys we're not quite here yet, and this is a fairly nuanced idea. But at the very least, for the solo growth model, what's crucial here, guys, is if you mismeasure labor and if you mismeasure capital, you will inflate your estimated TFP, right? And the idea here is just to go back to this equation. If you mismeasure this one and if you mismeasure this one, it will tend to increase this one, right? Your TFP growth. Because normally by mismeasuring we mean we will tend to increase this one too much or have a too high a measure of capital growth and too high a labor too high a measure of labor growth. Okay. So that is capital growth accounting, I should say. That's growth accounting. Okay. So we're trying to account for, in growth accounting, you're accounting for GDP growth from the sources of growth, which is the source of inputs, K and L, as well as in TFP. And TFP happens to be this residual, right? So in this section, the world of augmented solo economies, we will focus on the contribution of Mankiw, Romer, and Weil, and they used regression analysis to take or to estimate the augmented Solow model. And it's augmented because instead of just having regular physical capital, you will now have what's called human capital. Okay, how much investment in knowledge, right? Which is usually proxied by investment or expenditure in education or R&D. Okay. So here you have a Cobb-Douglas model N countries. Okay, each country is an island. The countries do not interact, except when they share some common technology growth. You have N countries. Okay, and notice here what we're trying to estimate. Here's capital with the expenditure alpha. And this H is now your human capital, right? This is now uh, a human, the non-physical capital investment in human knowledge that's embodied here in H. Okay. And then A times L, this is now your labor, which if you notice, there's an A here, which means we're thinking or we should be thinking about efficient labor units, right? A times L. Okay. So now you have three inputs, K, H, and L, right? And the coefficients in the Cobb-Douglas production function is alpha, beta, and 1 minus alpha, beta. So this makes it a CRS production function, constant returns to scale. There's a typo here. So this should be beta, not alpha. Okay, this should be beta. It nests the basic Solow model without human capital when beta is 0. So when beta is 0, this whole thing becomes 1, and it just becomes the usual Cobb-Douglas production function with alpha and then 1 minus alpha for labor. So you will have accumulation of physical capital. So you have a savings rate for physical capital, and you will have a savings rate for human capital here. So human capital and physical capital, they're pretty much they have the same law of accumulation or equation of motion, except that one accumulates physical capital and the other accumulates human capital. Like the standard Solow model, A dot over A is G. So that's just their growth in efficiency and labor, right? And then you can, as usual, define the capital per effective labor and now human capital per effective labor, because now you have two kinds of capital, physical and human. We focus on the steady state. So in the steady state, you have the following expressions for K star and H star. These are the usual steady state values for capital per effective labor and human capital per effective labor, which are usually derived in a Solow growth model. Okay, you can skip the derivation. It's not super interesting, but notice how similar they are. And they're similar simply because they're both capital. Okay. Consequently, this output per worker, Y over L, is going to be when you plug in K star, I should say, and H star into the production function, then you will get this expression here, which is an expression with savings rate. So The higher the savings rate, the higher the capital or human capital per worker will be, and therefore the higher Y will be, right? We've discussed this in class. The more you save, the more capital you have, the more your output will be. N, G, and delta, when these go up, your capital, your steady state level of capital or human capital will fall. And then notice you have your A here because this is output per worker. So output per worker is growing at the rate of A, right? If you recall that it's only capital per effective worker that have zero growth, but capital per worker will have a fixed constant growth rate in the steady state. Next slide. Right. So we know what Y star is. That's the output per capita along the balanced growth path. Okay. They make an assumption on technology, right? AJ is just AJ bar. So each country J will have different average TFP levels, but all countries will be growing at the same rate G. Okay. So A bar here will shift up and down, up and down. Higher TFP countries will have a higher Y star, and a lower alpha bar J will result in a lower Y star. You'll see that here. So this A bar J is kind of like a shifter for this one to make it move up or make it go down. Okay. This equation 6 is essentially equation 5 after taking logs, right? And you'll notice again how similar SK and SH are. The differences, of course, are the coefficients, right? So alpha happens to be the share of capital. So that's why alpha is here. And beta happens to be the share of human capital. So that's why the coefficient has a beta here for human capital. Delta K, delta H, and delta plus G is 0.05. These are the assumptions of Manker-Romer while. So basically, some of these numbers here, they substitute these estimated or calibrated, I should say, calibrated values. SKJ, this is data. This comes from average investment rates, investment over GDP. SJ is a fraction of school-aged population that is enrolled in secondary school. So that's a measure of human capital. Even with all these assumptions, 6 can still not be estimated consistently. So I just want to make sure you all note you have not done econometrics yet, right? So I don't expect you to truly, fully understand what's happening. The core thing here, however, is that in order to get good, so if you run a regression, right, the goal is to get this value, alpha over 1 minus alpha minus beta. So in the regression tables, we'll get the value of this entire thing as well as this entire thing. Okay. Now, to make sure that these coefficients here that you'll get are the consistent ones which approach the correct value, then you have to say that each element in this regression here, A, G, SK, and then SH, all of these are in a sense independent sources of variation or growth, right? That A bar has nothing to do with SK, right? And on average, nothing to do with SH, right? And nothing to do with G. Okay. So yeah, that's how a regression works, right? A regression is the best if each of these variables basically are all not necessarily uncorrelated because they can be correlated, but they're basically independent. That's the correct statistical word. Independent of each other. That in a large enough sample, um, if one goes up, there's no necessary reason that any of these will go up. Like sometimes they will go down, and so on and so forth. So there's no strict correlation, positive, negative correlation between any of these variables. Okay, because they're all independent sources of variation that all contribute to ln y star. Okay, so that's the secret, right? Therefore, the problem here is ln a bar j is unobserved, right? And thus will be captured in the error term. And ln aj, if it's in the error term, are correlated with the investment rates. So they're not independent of the SKs and the SHs. Okay. This At this point, you might pause and you think that totally makes sense, right? If your average TFP is higher, then that will incentivize you to save more, either physical capital or human capital. So this totally makes sense. And in that case, there are potential variables, this A bar J, which is correlated with the other regressors, the SK and the SH, the savings and capital, physical capital, and the savings of human capital. So again, this is not an econometrics class, but once you allow that sort of correlation between the error term, the uncaptured variables here, and the measured variables Sk and Sj, then you would get what's called an omitted variable bias and inconsistent estimates. Okay, so that's sort of a problem, right? And there's another crucial assumption here. It's called the orthogonal technology assumption, right? Which is basically what MRW or Mankey-Romer-Wiles answer to the endogeneity or omitted variable bias, right? That A bar is just EJ times A, where EJ is this independent variable or orthogonal to all other variables. So they make an assumption that L bar J is indeed independent, or this is another word for it, orthogonal to the other variables, and therefore they will assert that there is no omitted variable bias. Okay, so this is an important one. So please make sure to know that omitted variable bias is a problem when it comes to Solow, taking the Solow model to the data. Okay, because some of the things that we need to observe, such as TFP, are in fact unobserved. All right, so now let's get to the regression. So first we begin by estimating, the standard Solow without human capital. So in this case, alpha is the share of capital, then 1 minus alpha is the share of labor, right? So this will be the estimating equation. And notice that now you have this EJ here, which is your error term, which is assumed to be orthogonal or independent of these guys, and especially this guy, right? So there are no relationships between EJ and SKJ, which means if the assumption is correct, then we can estimate correctly alpha over 1 minus alpha. So what's our estimation? Let's focus here on MRW 1985, 1.42, right? This is their estimate for alpha divided by 1 minus alpha. Okay, so please check that if your coefficient is 1.42, then your implied alpha is 0.59, or let's say 0.6. Okay. So in order to check that, all you need to do is to calculate 0.6 divided by 0.4. And 0.6 divided by 0.4 is roughly 3 over 2, which is roughly this one, 1.4, right? 3 over 2. 3 over 2 is 1 and 2/3, essentially, right? 3 over 2. 3 over 2 is 1 and 2/3? Correct. No, wait. 3 over 2 is... It's close to 1.5. 3 over 2 is 1.5. So this is very close to 1.5. It's going to be slightly less than 1.5, and therefore it's going to be less than, slightly less than point, 0.6 here. Right. So make sure that you're able to connect it, right? This alpha here, this 0.59 or approximately 0.6, plug that into this alpha here. So it's going to be 0.6 divided by 0.4, or 3 over 2, roughly, right? Which is roughly 1.4. Then you can connect it again. Make sure that you are aware that this 1.01 means that you have an implied alpha of 1/2. So this makes more sense, right? This is easier. 1/2 divided by 1 minus 1/2, or 1/2. So 1/2 divided by 1/2 is 1. So that's why this is 1. Also notice that these are negative numbers here, negative 1.97, 1.12. Why is it negative? Well, that should come from here. There's a negative one here. And this is alpha over 1 minus alpha. Okay. So notice, however, that there's a problem, right? Because the coefficient of this one should be equal to the coefficient of this one. Right? And they're not super far, but they're not exactly the same either. And it jumps out to be more unequal here in the original work by MRW. This 1.42 should really be the same as 1.97, correct? Because of this equation up here. This should be alpha over 1 minus alpha should be the same as in value as alpha over 1 minus alpha. But in MRW 1985, they are not. And that's one of the clues that sort of led Mankiw to suggest that, maybe the standard solo growth model is not good enough, right, to take it to the data because these two numbers here should be closer to each other. Right. So now the most natural reason for a high implied value of alpha, okay, is that epsilon j is correlated with ln sk either because the orthogonal technology assumption is not a good approximation or there are human capital differences correlated with ln sk. So they favor the second interpretation. So they add another uh, capital version of human capital, shj here. Okay. And now they estimate this equation here, right? So now you notice that you have 1, 2, and it's really 3 because notice this variable here and this variable here, they're the same. So these slides didn't bother to put them together, but actually you can put them together and their coefficient will be negative alpha plus beta, right? Negative open parentheses alpha plus beta close parentheses divided by 1 minus alpha minus beta. So this should really be the sum of these two, right? Okay, so now let's go down. What did we notice here? So ln sk 0.69. The coefficient of ln sh is 0.66. And notice that you'll have those implied values of alpha and beta very similar to each other of 0.3. Notice that it's half, literally half. So half the alpha from before. So from before it was like a 0.5, almost 0.6, yeah. And then now it becomes 0.3. And beta takes up about half of the value, 0.28 or almost 0.3. So make sure you're able to get these values here, 0.3 and 0.28, from these values, 0.69 and 0.66, because that comes from this equation here, this alpha over 1 minus alpha minus beta, that is in fact 0.69. The other thing here is that the coefficient on N, G, and delta K, growth rate and labor plus G, which is assumed, plus delta K, which is the depreciation rate. The coefficient of this variable is alpha plus beta. So the estimate for alpha plus beta divided by 1 minus alpha minus beta is negative 1.73 here. So make sure that you're able to note that if you add 0.69 and add it to 0.66, add this one to this one, it should be the mirror image of this one. Should be very similar to the sum of this and this, which is the coefficient of 1.73. Okay. So note, it still doesn't really do a fantastic job, but it's much, much better. So 0.69, 0.7 plus another 0.7, which is what, roughly 1.4, less than 1.4. It's much closer to 1.73 here, right? So this plus this is much closer to this. Still not amazing, but much better than before. And that will also give you a better R squared, which they are mentioning in the text of this slide. Also, take note here, guys. Look at the number of observations, 98, 98, 107. So small observations and major implications on the data are totally consistent with each other. So if you have a regression with not as much data as, some modern regression work, don't worry, because even important macro work will require only a few, or will only have only a few data points available. So don't be too sensitive or too concerned about that. You can still use the data in a very useful way, even though the count of observations appears to be super small here. 98, 98, and 107. Even in 2000 with updated data, he literally just added 10 data points here. Now, if these regression results are reliable, they will give a big boost to the augmented Solow model, right? So the adjusted R squared is very high or higher than the older or the other regression. So this is 0.59 and they're comparing it to 0.78. Okay. And the coefficients themselves fit the theoretical Solow model much, much better. The immediate implication here is that TFP differences have a limited role, right? Specifically, if human capital, physical capital, N plus delta plus G, those three variables there, jointly, they all explain roughly two-thirds, or actually three-quarters, three-fourths of the data. Then that means one-fourth of the data is attributable to TFP according to these to MRW. Okay. But that's just one way to view it. And there's another sort of technique in which we will be thinking or studying, which is called calibration. Calibration is also uh, a variable or a technique that was done in GLS. All right. So now let's talk about calibration. So suppose that each country has access to the Cobb-Douglas production function here. So notice what you have here is Y or GDP is a function of capital and A times H. A happens to be the effectivity of labor, but H here is sort of a version of labor that uh, already reflects some kind of human capital associated with it, right? So there is no explicit human capital here, but it's also incorporated into H directly because each worker in country J has SJ years of schooling. And this SJ here is basically the exponent of theta SJ, which is again this value or number of years of schooling here times the number of people who experienced this level of schooling SJ at the country level J, right? So you can imagine, for example, the Philippines on average would have like 10 years of schooling. Therefore, this will be theta times 10, and then you will then multiply it with a labor force LJ here. So there's this exponent, literally exponent exp, which will shift up and down your endowment of labor based on the number of number of years of school that the labor force has on average experienced within the country J. So this is just a way to incorporate human capital into this measure of GDP in the Cobb-Douglas aggregate. Okay, next. So we'll skip a lot of this. Basically, we'll have estimates of K and estimates of H. Okay. Given your estimates of H and your estimates of K, where again H is sort of a schooling corrected number of workers, and KJ is your typical capital stock. Okay. You also need a value of alpha, and alpha again is the share of capital in output. So that's something that could be calculated using national income accounts. You will construct a predicted income at a point in time using this equation here. So notice what's interesting about this equation. Y hat, which is the predicted GDP of country J, is going to be a function of country J's capital, country J's schooling adjusted number of workers. But notice that it's multiplied by AUS, or the technology level of the United States. So we're going to use for all other countries the technology level that we get from using the technology of the United States. Okay, it's a prediction that let's say that all countries have the technology of the United States, given their endowment of capital and educated labor force here. What is the estimated GDP for that country? Now, AUS, or the technology of the United States, is computed so that Y, or GDP for the US, will exactly equal KUS, the capital stock of the United States, times AUS times HUS raised to two-thirds. Right? So AUS is a number that sort of makes sure that the left-hand side here, the actual US GDP, real GDP, is equal to the right-hand side, which is the Cobb-Douglas function here. Okay, so once you're able to do that for all countries, including the United States, okay, where again, all other countries, not the United States, use their own capital, their own educated labor force value here, but they use instead the USTFP. So once you've constructed this y hat j, it can be compared to the actual yj. Okay. So the important thing here, guys, is if y hat j, which again uses the US technology, exceeds the actual GDP of J, then that means, well, what does that mean? That means that using the US technology, that will give these other countries, countries J, a higher real GDP, which implies that their GDP, country J's actual TFP, I should say, is much lower than the US TFP. Okay. So once a series y hat j has been constructed, it can be compared to the actual output series to the extent that y hat j will be greater than the actual yj. Then that will represent the contribution of technology, right? In particular, if y hat j is greater than actual yj, then that means that US technology exceeds J's technology. So let's look at the data right now. Let's jump to the data. And this is calibrating productivity differences 4. And here you have the predicted log GDP per worker, right? And then this is the log GDP per worker, the actual GDP per worker. And this is the 45-degree line here. So that means if you're on here, the predicted log GDP is equal to the actual log GDP. And what do you notice here? You notice that the predicted is higher than the actual, which tells you that if you use US technology, again, to get this predicted GDP, it will turn out to be much higher. It will increase the country's predicted GDP. So that by using the actual GDP, using the actual GDP, we infer that their technologies is lower than that of the United States. Over time, so notice that these are numbers from 1980, 1990, and 2000. For all of these three graphs, most of the countries here are above the 45-degree line, which tells you that, in fact, the further along in time we are, the more clearer, the clearer it is that they're above the 45-degree line, and the higher this cloud is. And the higher this cloud is tells you that their technology relative to the United States is in fact falling, right? Becoming smaller. Or alternatively, the technology of the United States is sort of growing and leaving these countries behind. So that's what this means, right? Because that's how we constructed the Y hat. The Y hat includes US technology. Alternatively, you can back out country-specific technology terms. So using this equation here, you can focus on AUS and contrast that to AJ, which is the technology that is not US. So you can get the ratio of Y hat J for J, but this time with AJ here. And then you can divide that, say, by US GDP. Actually, I think it's the opposite. This is actually AJ. What is this? AJ. Oh yeah, that's right. This is why you can get this expression here by dividing y hat j, which is the production function of country j, by y US, which is the production function of the US, with both production functions now having the country appropriate level of TFP. So this one will give you this measure of alpha J over alpha US, or the gap, the productivity gap, or the TFP gap between country J and country US, which will be a function of the gap in real GDP between between J and US, the capital gap between US and J, and the gap of human capital between the United States and some country J. And we can go to the slides here. So these are the relative technologies, right? Which is again, the interpretation here, guys, should be the TFP of J divided by the TFP of the United States. And what we've shown here is that most of the countries here will have the TFP, a relative TFP, which is lower than that of the United States. Okay, they're below the 45-degree line. Okay, they're below the line here. So that will tell you that based on this exercise, this calibration exercise, countries will typically have different levels of technology, and that the fact that they have different levels of technology is important to determine their GDP per worker in all the three different decades that have been examined here. So if you notice that these results here are very similar to the GLS chapter on productivity, the role of productivity and calibration, and that productivity is the most important, actually, according to the calibration exercises, as a way of studying the Solow growth model. Differences in TFP is the single most important reason for differences in output per worker across countries. And specifically, all other countries, AJ over AUS, all other countries will have typically a lower value of AJ relative to the US. Okay. And that explains a lot in terms of their difference between their GDP, their real GDP, and US GDP. So this gap here explains a lot of the difference. And it's the same as in GLS as well. So that's the same sort of conclusion, that in order to explain differences in GDP per capita across countries, you will need to have large differences between a country's TFP and the US's GDP, US's TFP, right? I believe in GLS, the discussion there was uh, thinking about whether the savings rates can be used to reconcile differences in GDP per capita across countries, especially against or relative to the United States. And you'll find that it's not possible to do that unless you also assume major or large differences in TFP as well. All right, so that's our review of the empirical component of Solo, focusing a lot on three things, right? First, um, we looked at growth accounting. Second, we looked at Mankiw, Romer, and Weil in their what's called so-called Solo regressions on the long run or the steady state output per worker. And finally, we looked at the calibration method. Okay, and those are sort of the three things that can be done using the Solo growth model and bringing it to data. The final thing will be regressions on growth, which is the sort of the focus of our empirical investigation, which is an investigation on uh, convergence of growth rates between smaller, poorer countries and larger, richer countries. All right. All right, that's it for now. See you in school.